Okay, so our next demonstration is Niky, Riga, and Jeanne Ohren from the GENI project office. They're going to run a complete experiment in GENI and challenge you to do the same thing yourself.
So, hi. My name is Niky, Riga, and I'm with the GENI project office. While they're trying to connect the actual demo, I'll start with the presentation because I know we're low in time. So, the goal for this demo is to convince you that you can do an experiment yourself. It's very easy. It's like, as Mark said, if I can do it, any of you can do it, and hopefully you'll see it working now. So all the key pieces are in place. You've all run experiments, and you know what it takes to run experiment from beginning to end, design it, deploy it, take your measurements. And I challenge all of you to start using the tools, the GENI tools that are there. From my experience in GENI, I know that the best way to get what you need is to start using it and ask people. Everyone is extremely helpful, and they keep improving their tools based on your feedback. So start using them. You'll see it's not as hard as you expect, because I know that if you have been using GENI for a while, you might have the notion that GENI is hard. It's getting much easier. Thank you. So if you've been yesterday to GENI's session, the experiment lifecycle, you've seen this before, if it just formalizes what you already do when you're running your experiments. You first design your experiment, deploy it, you execute your experiment, you archive it, you tear it down, right? It's nothing. It's just a formalization of what you would normally do. In today's experiment, I simplified a little bit more. We're not going to run multiple runs. We're only going to run it once. And I'm going to describe very briefly the demo that I would like to do. So basically, the demo I'm going to do is to study the effect of network delay when I'm doing UDP-based file transfer or TCP-based file transfers. For UDP, I'm going to use UDT, which is a protocol that was proposed by Gu and al. And for TCP, I'll just use normal FTP. And this actually wasn't my idea. We had a paper last year in March in the experimenter workshop that some people did this more extensive study from a team at Madison, Kansas University, that they studied the performance of UDT and FTP in Emulab. So I'll start a little bit in the middle, just because executing the experiment takes time. So I'll start from the middle of my beautiful series of steps, and we'll start running the experiment now. So GENI will just start the command now. I used omniscripting because my experiment is very simple. I have very few nodes, and in order to instrument them, I wrote a small omniscript that will go log into my nodes and give instructions. And as the demo will go, you'll see the graphs there start changing, so you know that the demo is working, and we'll get back to it. So let's go back to my first step, which is design the experiment. As I said, this is a very simple experiment. We will have a server that will serve the files, a client that will request files either through UDP or through TCP. We'll need the link so that we can tune the parameters so that I can change the network delay between the two links. And then I need to monitor the performance of TCP and UDP to see what is the effect of network delay. So if you have done this before, then you can go ahead, find the GENI resources that you want and reserve them. If you are new to GENI and you haven't done this before, this is the point that you contact us at help@geni.net so that we can help you figure out what resources you need. If you already know, that's cool. You can go ahead, run your experiment. If you don't know, please send us an email at help, and we'll help you design this. So for this experiment, I will be using the proto-GENI nodes at Utah, and I'm going to be using the Gemini monitoring tool. So this is the topology I'm going to be using. It's a server and a client and a node in the middle that acts as my delay node. And we're going to have a monitoring node that will gather all the statistics and plot them. In GENI, as you might have heard before, I don't know if you will know it, is that all the topology, we tend to describe it in an XML document that it's called an RSpec. So this is where we can help you get the RSpec. In this case, my job was a little bit easy because this experiment that I'm just describing is one of the sample experiments we have on the wiki page. So I just needed to download the RSpec. And now we're going to go to the next step, which is deploy my actual experiment. Now that I have my RSpec document. So we're going to be using Flag, which is a web-based tool. And GENI now will go and create a new slice for my experiment. And after she creates the slice, which we might take a few seconds, then she will go ahead and load the RSpec document, and you'll see the Yes, that one, yes. So you're going to see the same thing I showed you in the previous slides. Now, if you press submit, if you press submit, then this will go ahead and create my experiment. This will take in the order of 10 to 15 minutes, which we don't have now. So we have another slide that we have already created, and it's already there. I think, yes, this one, yes. So you see now my background is green, and I have already reserved my slides. Now, the next step is to actually set up my monitoring. So as I said, we're going to use Gemini. And in order to set up the monitoring, I just need to run one command line tool. If you have the VM that we have been using for the tutorials, then you just need to go there, set up your environment, which is extremely easy, and then just run one command that is instrumentize. And when this is done, in the end, it will print the information you need to log in to the web portal and start monitoring your traffic, which you see there, all the information that was printed by the Gemini tool. So now if we go back and log into the portal and see the portal, this is the information. You put everything that the Gemini told you, and you press map your slides. And this will bring you here, and from here you can go back to the graphs that we were actually seeing before. So, and as you see now, my experiment is running. So the next step will be to execute my experiment. As you remember, I've already done this in the beginning, so my experiment is already running, so I will move to the next step, that is analyze my experiment. So as you see there from the graphs, hopefully these two graphs look kind of similar, what we see is that for UDP, as we change the delay, the performance is more or less the same. You see a spike, all the traffic goes there, the performance is not really affected by the delay. But if you look at the TCP graph, as we increase the delay, TCP takes more time to wrap up, so the transfers there get much shorter and wider. It takes more time, and it managed to get less bandwidth. So, and there we also see the aggregate interface traffic. And we do one transfer at a time, one UDP and one TCP. So we don't want them to interfere one with the other. So we can see, and I can monitor my experiment while it's running. And then let's say I'm done. This is my experiment. I want it. I'm done. And then I want to archive my experiment. So now GENI will go back to the portal that you saw before that had the map. And from there, there is a button that you can press, and will actually archive all the results that you have on your experiment. And so you'll just have to select the node on the top. Yes, and then, yes, put my information there. And press the archive to iRoads, and this will take all the data from your experiment, including your RSpec, modification on your nodes, the IP tables, everything, and we'll save it in a server that you can go later and access them. And I've already done this before, so I ran an experiment yesterday. You'll see the date there, and I've already done that, so we'll see what information you can access from there. So the first thing is your graph, so let's go and see the graphs, and you'll see that they look very similar to what we just did. If you go to the TCP graph there, it will load. Anyway, it will load, and you'll see that it's very similar, and it also gives you a link to the file so that you can actually download it. There you go. It's very similar to what we just saw. And then it also has your RSpec. And you can also, if you want, you can download the measurement that it was taking in a RRD database format, so that you can download the raw data and do your own analysis on them, if you want to plot your own or different graphs. So now I have archived my experiment, and I have it. And now it's time to tear down my experiment, because I'm a nice experimenter, and I want the resources to be free for other people to use, now that I'm done. So we'll just go back to FLAC. Our experiment has already been deployed, the other one, and we can go ahead and delete it. OK. So today, I've used some very few tools that are available in GENI, just because I needed to choose something, but there are many more resources and tools you can use. So I use ProtoGENI, but you can use ProtoGENI, the InstaGENI, or the ExoGENI racks. There are Planet Lab, OpenFlow resources, wireless resources, and many more. For deploying my experiment, I use FLAC, but there are other tools out there like Omni. To monitor, I use Gemini, but again, there are other tools out there. There is GIMI, where there is a tutorial tomorrow morning, which I suggest you all go and see. There is OMF, OML that the WiMAX tutorial will go and cover. And I mean, you can see here the list of experiments. And there's still more tutorials for the rest of the GEC, so I suggest that you try and attend as many as you want so that you learn these tools and you start using them for your experiments. So in summary, run GENI, start using it for your experiments, and you can do this yourself. It was very easy to set up. I just needed 2 accounts. I used 4 different tools that were very easy to set up and use. I just needed 2 files, 3 commands to run, and that was it. And I have all the instructions of how I did this online. So please come to the experiment and drop-in session that is today from 3 to 5 p.m. and try it out. I'll be there to help you if you have any problems. That's it. Thank you.
Now I know we call it the GENI race. That was the fastest experiment ever. But the key point here is there were not big pieces missing. You can run the same experiment, follow the same instructions, and all the key components exist now in GENI. You can discover your resources, you can run your experiment, you can do analysis, and you can archive the results for later. Joe, are you here? Excellent. So our next 2 presenters are going to talk a little bit about some international collaborations that are ongoing with GENI. Joe Mambretti is going to give us an update on Slice Around the World. And you'll recall that Slice Around the World is sort of helping us to understand the large-scale vision. What can we do as a member of a large international collaborative to enable major experiments around the world. After Joe and Jim give their demo, Aki Nakao will come and he will give us an update of some work that he's been doing, and he's going to show us a particular deployment of an experiment that runs across the VNode system in Tokyo, some proto-GENI systems here in the US. This is another experiment laid out over a very similar topology to the XIA topology that we saw earlier today. So, Joe.
Okay, thanks for that introduction. Jim is going to do a demo in a bit. So you got a little bit of a flavor of what the Slice Around the World is, and I'm going to explain it a little bit further. Basically, there's a lot of different activities here, but Mark said it exactly right. It's a collaboration among many international communities working on very similar things. The basic goal is to create a large-scale distributed environment, a platform, if you will, for basic network science research, experiments, and demonstrations. So we are designing, implementing, and demonstrating in a variety of formats a international distributed environment that can be used for next-generation communications. Certainly it's more than a network. There's many resources available and many coming, and the environment is based on interconnections among basically network research centers. We found that the people of the highest degree of interest in this are network research centers, and we have quite a few collaborating that I'll mention. And have to give credit for Chip Elliott for the concept here, saying, hey, wouldn't it be a good idea to do a Slice Around the World, and has launched this effort, so thank you, Chip. A big motivation here is recognition that in addition to the GENI project sponsored by the National Science Foundation, there are many other fine projects around the world, such as the European Union Future Internet Research Environment and the Japanese New Generation Network, the Korean Future Internet, the G-Lab at Kaiserslautern, and many, many, many others. And we want to take advantage of these activities and work in a collaborative way. So there are different pieces to the initiative. One is implementing an initial environment that has the resources, as I said, and then designing and staging a series of demonstrations that illustrate the power and capabilities of these fabrics. And of course, we're always expanding the resources and implementing enhancements. The categories of activity seem to fall into three main buckets. One is applications and services, and you'll see some of those here. Another is underlying middleware and the programmable environment. And then there's the actual international foundation resources. This is a list which I won't go down of those people who are collaborating in this initiative. And as a background foundation to this, we have the Global Environment for Network, the Global Lambda Integrated Facility, which is a great environment within which you can create private networks and test beds, and we do this routinely. So that's already up and running. We have agreements in place. We hosted with the University of Illinois at Chicago, in Chicago a couple weeks ago, the annual meeting, and we had lots of discussions about GENI and connecting GENI more closely with this environment. We were pleased to have Chip Elliott as one of our keynote speakers, and there's a great deal of interest in this community to support the GENI efforts and the related efforts and the collaboration among all of those activities. I'd like to mention specifically also a partner in the GLIF is Gloriad, which is a National Science Foundation funded project which is creating an international fabric, which also is very much a GENI supporter, and we're leveraging them. This is a fabric that we have up and running today, and I'll have to note that we were very proud to bring in Ruslan's facility just a few days ago. That's represented here by the logo of Moscow State University because that's where he's from, but it's actually a technology research center focused on network research. We'll be continuing to expand this. These are persistent capabilities. This doesn't go away tomorrow. We're continually building these as a persistent fabric. So on the application side, we've been having a series of demonstrations, and one of the applications that we chose to show at a variety of formats, including at Paul Mueller's workshop in Würzburg, is a capability for using programmable networks and programmable clouds to look at objects that would otherwise be invisible. Mark told me to be aware of the time, so I'm not going to go into great detail here. And I'll note that this is a slice using forwarding rules based on content. It's basically a content distribution network for nanotechnology, a viewing scope for nanotechnology. Also, we're working with Rick McGeer on TransCloud, and he showed yesterday at the demonstrations TransGeo, which is an open distributed federated GIS system. And it's a very clever capability, and one of the things he's doing is measuring the greenness of cities. We're working with Aki and his packet caching. We helped him with some VLANs, and we expect to do a lot further with Aki and his VNode resources. We're planning a series of demonstrations for SE12. This is an international open flow fabric that has been established by a number of folks. The SE12 is a really good forum to do GENI type showcases because they have massive capacity. I think they're bringing 600 gig there now. We have 100 gig dedicated and 100 gig on the show floor coming. They are very supportive of OpenFlow, so we're going to have OpenFlow on the show floor. And Jim is showing this international testbed. So it's an international OpenFlow testbed, not to do one experiment, but to do a whole lot of experiments. So we're going to show multipath TCP, we're going to show information-centric networking, multi-domain OpenFlow topology discovery management, multi-layer OpenV switching networking, and content-centric distributed networking. And there's a paper on this that has been accepted for publication in the SE proceedings. This is the content-centric network distribution network. This is the information-centric network. There's another paper on some other aspects to this, including the multipath, that have been accepted. And again, in interest of time, I'll go right to the demonstration that Jim is going to show. Go for it.
So I think most of you see this already. So what you see here is Opinion Banking, which is
So I think what you see here is an experiment running. Okay. So you can see that the light goes through the object and not goes through the object. And I think it's because the wireless, if I turn it, you'll see, okay, it's trying to catching up. So we write a program in a way it will go through different passes, and while it's catching up, I'm going to show you how this works. You can see we have probably a bunch of different experiments here, and we distribute data around the world. As you can see, there's a different sites. Some of it is just from iCare, some is from HP Lab, some is from HIC Academy of Sciences, is Russia, Moscow, and Kaiserslautern in German, and Utah, and Kaiserslautern again. So I think when I come back, it will catch up. So now you'll see all the data get archived and displayed. This is one of the experiment. We're going to try the other one. Stop this one.
While you're stopping that and starting the other one, I'll note that we're working with nanotechnology researchers on this who are creating new components through engineered materials that are putting functions that are today in very expensive external components to the optical part of the network, and they're engineering the fiber so those functions are taking place within the network itself. And it's changing from something that may cost $100,000 to something that costs a penny and a half, because the function is actually in the fiber, it's built in the fiber. So in order to do that, they need to have a viewer that allows for viewing of very small materials. Before this was put together, they had to do rendering over long periods of time. Now they can do real-time steering of their experiments by having the capability of the programmable networks, programmable clouds. So go ahead, Jim.
So this is another experiment for the silver particle chain. So you can basically simulate how the wave goes through it, and how the wave interact with the silver chain, and how they reflect to each other. Because the key here is really in the nano world, all the physical parameter is a little bit different in the traditional world, because in the nano world, static and some other factors in there is a little bit different. So it's not interact as well.
Yeah, so he's actually live changing the variables here to have a different type of experiment.
Yeah. Go back a little bit to what we're doing here. We actually archive all these images and experiment at a different site. And what we have here is really a program look at the request stream and decide where we should send the request to, and get the data come back to the interfaces here. So this is live, goes to wireless, and so if you have any question, we can talk more after.
So just another word on nanoscience, why it's so interesting and why it's an important science today is that the normal laws of physics do not work at the nanotechnology level. So things are reversed. So things that normally don't conduct electricity do, and things that normally do conduct electricity don't. So things radically, fundamentally change. It's a very exciting science, and some interesting work being done. So what are the next steps? Well, there's this next presentation coming up, which is working to some degree. Aki's people are working on integration of the VNode technology and Rob Ricci's proto-GENI. So that integration, federation, expanding of the integrations internationally, many expansions for functional capabilities, functions and capabilities, and many more demonstrations. We're planning to partner, of course, with the InstaGENI project as the racks get deployed, also with ExaGENI. We have a very large and growing demonstration schedule. And with that, I'll say thanks. And we have 1 minute, 28 seconds left. So if there's any questions, thank you.
Thank you, Jim and Joe. So we've just got such an abundance of interesting stuff going on that I recognize are consuming lunch, but this is our last presentation, and it's a really good one. And we're going to see a little bit of a report on some of the work that Aki's doing in his lab back home, and we will see the promised demonstration of a federated VNode proto-GENI system running a packet caching scheme. So, thanks.
Mark, where's the display? Hi, I'm Nakao from University of Tokyo. So today I brought two persons who helped me with the demo, and also in Japan it's like 2 a.m. and there are still people in my lab and other places to support this lab watching all this demo. So the title of my talk is Federated VNode, GENI, and Packet Cache Demonstration. And this is not, the packet cache demonstration is not the center to my presentation. It's more about a federation that Mark mentioned. We have a VNode system in Japan, and we were federating VNode, GENI over Pacific Ocean. So just briefly, I want to introduce our project called VNode. We started in 2008. And for the first 3 years, we developed the first version of VNode, and the second round started in 2011, and now we are building a second version. So the architecture is very different from proto-GENI or any other GENI testbed architecture, but we have very similar piece. Here is a portal that you can go and create a slice, and goes to domain controller, which is sort of like CM. And we have a bunch of VNodes connected. And also we have something called network connector, which connects the external network into a slice. And also we have access gateway, and where we can connect the edge terminals into a slice. And I can go into the more detail, but due to the time constraint, I'm skipping all these detail. But just like InstaGENI and ExoGENI, we have this rack of machines. We can inject a program in a slice and run it all across Japan. So right now we have 7 VNodes and 4 network connectors and 11 access gateways running in Japan, and we are using this infrastructure for slicing and injecting programs and running new network services, just like in a GENI project. And Joe gave a nice presentation about Slicer Around the World project, and so as part of this initiative, we exported our VNode to Utah. It took us over now 3 months, is that right? And we had to do a lot of paperwork, and Rob had enough of that. So, and finally, we moved one very small VNode called NC to Utah. Now our VNode is sitting in the lab in EmuLab, and now we are doing an experiment over 2 testbeds. And now I'm reporting how we did that. So this is the federation architecture that we have, because we have a very different architecture than proto-GENI system or any other GENI system. We need the component called a SEP, slice exchange point. This is like an exchange point, like in the current internet, but it translates APIs from GENI, from proto-GENI to VNode, or VNode to GENI, in the same way. And then, so we wanted to put this piece in Utah Emulab to connect our VNode system and proto-GENI system, but we are not there yet. So today I'm showing that we developed this SEP already, but we are not putting that into Emulab yet. So today I'm showing only a data plane federation part. This is just a half of this, what we wanted to achieve. It's called NC, and we put this NC in Utah, and we are connecting our two testbeds. So this is, to the best of my knowledge, this is the first trial of creating a slice and running an application on top of these two testbeds. So in order to do that, we had two options. Putting one VNode in Utah. So this NC7 is the one that we put in Utah. And as a backup plan, we placed NC10, which is part of VNode system in Tokyo. And due to, because we wanted to do this second option, the first option, NC7 in Utah, and create a slice over NC7, but because we couldn't do that, so NC7 is already set up, and we are ready to do that. But today I'm showing that, the slices, two slices created over NC10. So by looking at this picture, our slicers created on top of JGNX, JGNX DCN, going across a Transpac 3 network, and a DCN again, and Internet to ION, and Emulab, UAN, quite a bit of networks we are going over. And then we are connecting that. So earlier today, we had a very impressive demo done by CMU Fox, XIA, and that slice is actually running on top of these two testbeds. So in the background, we created this slice, and we have been debugging, this setup for like 2 weeks or 3 weeks. We exchanged like over 100 emails. Okay, and we are running packet cache slice as part of my project. Okay, so we consider two options here. NC10 in VNode, we are creating a slice over NC10, or we are creating a slice over NC7. There's good and bad. So because we are using GRE tunnel to create slice, so we have to translate VNode VLAN ID to a GRE key at some point. So if we put this translator in NC10, so then you have to have a lot of VLAN going on between US and Japan, so over Pacific Ocean. So it's not very scalable. So ideally, we want to put this translator of a VLAN ID to a GRE in Utah. So next GEC15, so maybe we can create as many slices as we want, but we keep only a single VLAN ID connected between US and Japan. Okay. So this little picture is the VNode, installed in Rob's lab, and I'm showing a little video. So this is our lifeline. So this is going from, this is going. I don't know how to play this one. Okay, so this is our lifeline. So this is an InstaGenie rack, and it's going to the ceiling of the Emulab, and then going to Internet 2. So if it breaks, sorry, Rob, I didn't ask you for your permission to put this video up. Okay, but we are having a lot of fun debugging together. Okay. So now, getting back to my slide. So the packet cache that we are running in my slice is, works like this. It's very simple. We have egress cache node and the ingress cache node and egress cache node. So because the packet length is variable, so it's very hard to cache. So what we did is that we chop up this packet payload into smaller pieces, and we keep track of this offset, of the alignment of the 128 bytes, and we take 128 byte chunk and take a hash, and replace this original content chunk with hash value so that we can compress that packet, and we keep track of which hash value corresponds to which original chunk. And by doing this, we can compress the packets, drastically, like 1/5 to 1/8 of the traffic. So the entire picture of this packet cache slice is like this. From Kyushu node in VNode, southern part of Japan, we have a bunch of nodes, and the packet, we have a file server sitting there, and GENI, we create a file download client here, and this client is gonna download the content going across the Pacific Ocean and going through our VNode slice to get to file server. But in the middle, we are putting a click version of ingress cache and egress cache so that we can compress the packet data to 1/5 over Pacific Ocean, because we are demonstrating that we are reducing peering traffic drastically when we are when a bunch of clients are downloading the same content over and over again. Okay. So this is our packet cache slice configuration in GENI. We have cache egress and clients set up in a FLAC interface. And this part is going to Japan. And we have a packet cache slice configuration in VNode as well, and we combine these two slices. And in future, we have like a unified interface to create a single slice over two testbeds, hopefully. Okay. And now we are measuring traffic at this point, just after the file server, where the original content is flowing, and also right here. We are observing the compressed packet. So you see the difference in the packet size. Okay, and for that, we are using a Prestat, 10G packet capture NIC, and this is amazing. This is developed by NTT folks. One of them is sitting here, and it can capture at the 10G speed, and the packet capturing time. Stamping granularity is 100 nanoseconds, so it's done by FPGA, and it's put in a VNode infrastructure. So we put Prester packet capture here and here, so we can tell the difference between a bandwidth that we see just after the file server and over Pacific Ocean. So now, hopefully, the demo is working. So this, this screen is showing, we are serving the packet traffic bandwidth, and blue bar is showing like original packet flow, and the red one is compressed packet flow. So like the other impressive demo, so I'm showing only this picture, but it's actually, so I'm glad that it's actually working, and it's compressed like 1/8 of the the traffic, and for this just one graph, we worked very hard in the past 3 weeks. Okay, so I want to, if I have time, I want to give a little bit update on the Flare, and we worked on this Flare architecture, and I presented this in the last GEC15, and we actually virtualized the switch, and you can have, in a single switch, you can have up to 15 layers of slivers so that you can inject a program in each sliver. And I'm advertising that I brought the real Flare switch, so it's like very small, and if you power it on, it's very quiet. and low, it consumes only a 200 watt. It got 4 10G ports here, and you can create as many as 15 slices. And in each slices, so we can inject a program, and if you're grad students and also postdoc, you can do a programming using Click, and this is the implementation that we did for OpenFlow switch, and the performance number is very impressive. So for Ethernet switching software done in Click, we can hit like 10G with just 1 core. So inside this box, we are running a mini-core network processor, and using only 1 core, we can achieve 10G performance, and with the 1500 bytes MTU. And OpenFlow switch is a little bit complex piece of software. We ported this OpenFlow switch software in Click, so it's done in a Click element. And if you take 3 cores with a 1500 bytes packets, we can achieve 10G switching. We are doing exact MAC address matching. So if you want to do like wildcard matching, or if you want to do more complex pattern matching, so then maybe performance may be degraded. But we are doing extensive performance evaluation right now. But nice thing is that you can do Click programming on top of our platform, and it looks like a Linux VM, and you can run your own Click element and add it to your OpenFlow element, and doing some interesting and complex stuff. I'm just putting this here. I don't want to drop it. So in summary, so the data plane federation is just started, and also control plane federation. Maybe next GEC we're gonna try. We want to convert from NC to slice exchange point software, and more geographical distribution. Mark is planning a more worldwide scale, and Joe is talking about slice around the world. So literally, maybe we can extend this activity to more places like GLab, for example. So, and more applications, packet cache, XIA. XIA is very interesting and non-IP protocol experiment, and we see also more applications on our testbed. And also, I want to use this flash switch in a proto-GENI, and maybe we can federate this nice piece of hardware and connect that as well to a proto-GENI or other GENI system. Thank you very much.
Thank you, Aki.